Alright, so last time we were looking at a heap. So a heap could be a max heap or a min heap. And I said there are two requirements for a binary tree to be called a heap. So the two requirements are what? The binary tree has to be, first of all, what is called essentially complete or complete. And then with regard to the data of the nodes, we can call the heap as either a max heap or a min heap. So in a max heap, the data for any internal node should be greater than or equal to the data of its two child nodes. Whereas in a min heap, the data for any internal node should be less than or equal to the data of its two child nodes, or one child node if it has only one child node. So again, this what is essentially complete property means is, if a binary tree is of height h, it should be a complete binary tree up to level h minus 1, which means the level previous to the last level. It should be a complete binary tree. That means every internal node should have two child nodes, and in the last level, all the nodes should be to the left, as much to the left as possible. So these two binary trees here are essentially complete binary trees, whereas this one is not essentially complete, because even though it is a complete binary tree up to level h minus 1, at the last level all the nodes are not to the left, as much to the left as possible. So here we have this node with no child nodes, whereas these internal nodes have child nodes, so that's not acceptable. Whereas in this case, in the last level, the nodes are as much to the left as possible, but still it's not an essentially complete binary tree, because the other condition or requirement that the binary tree should be complete until level h minus 1 is not applicable here, because at this level h minus 1 it is not essentially it's not complete. So a binary tree that is complete up to level h minus 1, and in the last level h all nodes are as much to the left as possible, can be called an essentially complete binary tree. So now what we are going to do today is how to check, given a binary tree, it is essentially complete or not. So we are going to use the breadth first search algorithm for this. So we saw the breadth first search algorithm in the previous module on binary trees. So we are going to just make use of it. And if you remember, there we used this queue data structure to store the nodes that we visit. So we are going to do the same thing. So, and again, this is a programming assignment, so please pay attention to it. So I am giving here only the pseudo code, and the real code is going to be almost the same. You have to just convert this to a C++ code. Alright, so we use a queue to keep track of the vertices that have been visited. So this could be an integer queue then. So this is an object of class queue, and we start with, again, we are going to assume the convention that the root node ID is 0, and that's how we start the breadth first search from. Now again, you may wonder, where is the data here? There's no data shown here, because I am showing here only the node IDs, because that's what you need to traverse the binary tree and check if it's essentially complete or not. So the data comes into picture only if you want to check if it's a max heap or a min heap. So that's why the data is not shown here, just to keep it simple. Okay, so we have the node IDs to traverse. So we enqueue the root node ID 0 to the queue. That's the first node that is added to the queue. Now we are going to keep track of a boolean called no child zone starts. So what I mean here with this boolean variable is, let's quickly look at this example. So if you remember how you do breadth first search, you do in a top down left to right fashion. So that means you first start with the root node 0 and visit its two child nodes, which are 1 and 2, and then visit the child nodes of node 1, which are 1, 3 and 4, and so on. And then for 2 it is 5 and 6, and then for 3 it is 7. So we start top to down, left to right. So for node 0, we find that it has both child nodes. It has left child as well as a right child. Then node 1, it also has a left child as well as a right child. Then node 2, it has a left child as well as a right child. Then node 3, it has a left child but not a right child. So this is where we can set that boolean called the no child zone starts to be true. So until this point it is going to be false in our code. So once we come across an internal node that is missing a child node, we can set that boolean to be true. Then once it is set to true, every further node that we are going to visit should not have any child node. So we start with 0 and 1 and 2 and then 3. So the no child zone starts boolean is set here because 3 doesn't have a right child. Then we will visit 4 and 4 doesn't have any child node. Then 5 doesn't have any child node. Then 6 doesn't have any child node. Then 7 doesn't have any child node. So every node that we are going to visit after this boolean is set to be true should not have any child nodes. If any node has a child node, which means it happens to be an internal node, then after the no child zone starts boolean is set to true, that is a violation of the condition that the nodes in the last level are as far to the left as possible. Or it could even violate the requirement for being a complete binary tree at up to level h minus 1. Okay, so basically, so let us try on this example here. So if you start from here, this node has 2 child nodes, so no problem. This node has 2 child nodes, fine. This node has 2 child nodes, fine. This node has both child nodes, fine. So now this node doesn't have a left child. So the no child zone starts will be set to true at this point. Now when you visit this node, it has a child node, so that is a violation because this indicates that this node has child nodes that are not as far to the left as possible. Let us try on this one. This node has 2 child nodes, fine. This one has 2 child nodes, fine. Now this one has only left child, no right child. So that means the no child zone starts will be set to true right here. So now you visit this node, you see it has 2 child nodes. So that's a violation again, because that means here that means at the earlier level h minus 1 the complete binary tree property is violated. And for that reason this is not essentially complete. So basically the idea we're going to use is once we come across a node that doesn't have a child node and we set that boolean to be true, every further node that we traverse should not have any child node. So that is the simplest way to look at this. Okay. So let us look at the pseudocode and use this example. We run this breadth first search algorithm in a loop until the queue becomes empty. So we have added the root node ID 0 to the queue, so the queue is not empty. So we get inside and we dequeue. So the node that is in the first node in the queue comes out. So that's I call it as the first node ID. So that's the ID of the node that is dequeued. So the root node ID is dequeued here. So now what we do, we check if it has a left child and right child. So that's what we're going to do. So the first we have to check if it has a left child. Okay. So it is again violating the essentially complete requirement. If a node has no left child but has a right child, then that's not an essentially complete binary tree again. Alright, so first we check if the node has a left child. So this is how we check. So we initially set the no child zone starts boolean to be false. So if it continues to be false, so that means we have not yet come across any node with a missing child node. Okay. Then and first node dot left child node ID is -1. So that means the node that we just dequeued from the queue, we find out that its left child ID is -1. So again, if you remember in the class, we follow the convention that if a node has a missing child node, the ID of the missing child node is -1. So if the left child ID of this node that we just dequeued, which means we're just visiting that node, is -1, that means that node doesn't have a left child. So it is time to set this boolean to be true. So no child zone starts is now set to true. So until now it is false, it is now set to true. else if, that means if this combination of the condition both don't evaluate to true, else if no child zone starts is true, that means that Boolean is already true. That means we have already seen a node that has a missing child node. So that means, as I said before, every further node that we visit should not have any child node. So now look at the condition here, and first node dot left child node ID is not -1. So that means this node that we just dequeued happens to have a left child whose ID is not -1. So that means the Boolean is already set to true. That means you already come across a node that has a missing child node, but further down we come across a node that has a child node. So that is a clear case to indicate that the tree is not essentially complete. So you can right away stop the code and return, say, if you are returning, say, a Boolean true or false, telling it's essentially complete or not, we can return false, means it is not essentially complete. So these are the two of the four conditions actually that we need to check. So what are the four conditions? You see here there are two variables. One is the no child zone starts, and whether that first node has a left child ID or not. So I have listed here the four conditions. So the no child zone start could be either true or false, and the left child ID could be either -1 or not -1. So depending on this, there are four possible combinations. So what we just looked at is no child zone starts is false and left child ID is -1. So that is this condition. No child zone is false until then, and the left child ID is -1. That means just now the no child zone has begun. So that's why we set it to be true. That's the first combination of the conditions. Now the second one is no child zone starts is true, and the first node has a left child, which is ID is not -1. So that is this first condition. No child zone starts is true and the left child exists. So that is a case where the binary tree is not essentially complete. Okay. So we have to now cover these two middle conditions here. So let us see what this condition looks like. So here we say if the first node dot left child ID is not -1. So it means the node that we just dequeued and looking at its child node, and we find out it has a left child whose ID is not -1. So if you see the second and third, that these are two conditions that are to be covered. The third condition is where the left child ID is not -1. That means left child exists, and the corresponding no child zone starts condition is false. So that's why I did not explicitly say that, because it implicitly follows once we check the first two conditions, if else if, then we have this if here. That means if you have the child ID not -1, that means the no child zone starts will be also false. And what that means, no child zone starts is false means so far we have not come across any node with a missing child node, and this current node we are looking at also has a left child. That means everything is fine so far, and this node is also fine until now. So we just continue, and so we now enqueue the left child node. This is part of the breadth first search process. When you visit the node for the first time from a parent node, you enqueue that node, which is the child node, to the queue. So add that child node ID, the left child node ID, to the queue. So now that means you see here, if the control goes further, that means what? That means this condition of course was not met. Either this was set to true, so that's fine, and so no child zone starts is set to true, and so I didn't explicitly put the fourth condition where the no child zone starts is true and left child ID is -1, because that will be automatically the case if you happen to continue further down without going through any of this inside any of these three if statements. Okay. And you see what does that condition, second condition, means. No child zone starts is true. That means no node so far has a missing child node. No child zone starts is true means some node has a missing child node, right? and the current node we're looking at also has a missing child node. So that's what the second condition means. So no child zone starts is set to true means some node already has a missing child node, and the current node also has a missing left child. So that means we'll just continue and check further any node has missing child or not. Okay, so this is how we check if the node has a left child or not, and accordingly change the boolean when it's needed. And also we can check if the tree is essentially complete, not in this case. Okay, so now we have to do the same thing for the right child. So the same set of conditions for the right child. So if the no child zone starts is false, so that means no node has a missing child node until then, but this node has a missing right child, so set that boolean to be true. Else if some node already has a missing child node and this node has a right child. You see, right child ID is not -1. That means it is having a right child. That's the case where you can return right away the tree is not essentially complete. Then if the node has a right child ID, then according to this table here, that means the no child zone starts is going to be false. So this is the case where we can enqueue that no right child ID to the queue, because it is okay. The no child zone starts is false. Everything is fine so far, and this node also has a right child. So just keep going. And the second condition, which we don't check here, again we don't check for the right child, because it implicitly means that if none of these three conditions are met, that means the no child zone starts will be true, and the current node also has no right child. So this is what we need to keep checking and run through this while loop. So we start with node 0, and we see it as both child nodes, so the node zone no child zone starts will be still false. Then with 1 it has two child nodes, so the no child zone starts will be false. Again 2 has two child nodes, so it will be still false. Now 3 has only a left child. So when we visit at the child nodes of node 3, it has a missing right child. So no child zone starts is false, but it has a missing right child. So this is where the no child zone starts will be set to true. Then we visit node 4. The no child zone starts is already true, and it has a missing left child, which is this case. The second condition, no child zone starts is true and missing left child. So none of these three conditions will be true in that case. And then it has a missing right child either, so none of these three conditions will be true in that case. Then again for node 5 the same thing, node 6 the same, 7 again, so on. So once we visit all the nodes, we can come out of the loop. So if we have not exited from the program until then, it means everything is fine so far, because that's what the second condition means. If the no child zone starts is true, and the current node looking at also has a missing child node, keep continuing. So if you keep continuing until and then you come out of the loop, it means you have traversed all the nodes and the conditions have been met. So that means we can return that the binary tree is essentially complete. Okay. So I'll stop here. If you have any questions for a second, you can send a message. I'll convert this to a video.